This video will overview how to approach identifying oxidation and reduction within a redox reaction. Before we begin, there are some things to keep in mind having to approach. First, solids are always going to have a charge of zero. They're never going to be positively or negatively charged unless it's absolutely stated, but solids, where it's denoted by having an S in parentheses next to the molecule name, they're always going to have a charge of zero. You have to calculate the formal charge of each part of the molecule. When I say the part of a molecule, I don't mean the elements. You have to determine whether or not it's an individual element that's moving or whether or not it's like two elements or more elements bound together that are all moving as a unit. So to that point, some molecule parts have formal charges easier to memorize. For example, a sulfate ion is SO4, but the way sulfur is set up, the d orbital is able to bind with all kinds of different things. So it's basically just able to make more than 4 bonds with other molecules without the charge being off. And so sulfur, phosphorus is another element that's like that. And so there are some molecules where it's just easier to just memorize its formal charge overall. Sulfate has a formal charge of -2. In order to figure these things out, it's easiest to separate these into half reactions, where each part of the molecule that's moving becomes its own reaction with the products and reactants. You also want to make sure you are tracking the movement of hydrogen and oxygen, but the movement of hydrogen and oxygen in and of itself is not the relevance of whether or not something is oxidation or reduction. You have to focus on where the electrons are moving. And to that point, it is easiest if you separate the movement of a hydrogen ion from an electron itself to determine, oh, did the electron move with hydrogen? Did the electron move separately from the hydrogen? It's not about where hydrogen's moving, it's about where electrons are moving. So given this example, if you have zinc as a solid that's combined with copper sulfate, which is in an aqueous form, so it means it's dissolved within water, you're going to get zinc sulfate, which is now the zinc bound to sulfate dissolved in water, and copper as a solid by itself. The first thing that we got to do is check out the formal charges. So for zinc is a solid, and as we previously stated, all solids have a formal charge of 0. And that also checks out with the above charge. The charge overall assigned to zinc as a molecule itself. Copper sulfate is 2 different things bound together, copper and sulfate. And so I have to separate those 2 into what their formal charges are going to be. And metals in general, in addition to sulfur and phosphorus, are very difficult in figuring out what is their actual formal charge. It's going to depend on what else they're bound to. So the sulfate ion we discussed has a formal charge of -2. And so because this overall copper sulfate has a charge of 0, or you don't see anything in the superscript or like above the letters, we have to assume then that copper is carrying a charge of +2 to balance out the -2 of the sulfate for an overall charge of 0. And that's both on the reacting side. Then on the product side, we again see the copper as a solid. And so because copper is a solid, solid has to have a charge of 0. We also now see the zinc with the sulfate. The sulfate ion is still -2, so we're going to keep that as -2, which then means the zinc has to carry a charge of +2 in order for the overall molecule charge to add up to 0. So now that we have each of these, we see the copper, we see the zinc, and we see the sulfate. We can separate these each into their own reaction to see whether or not electrons are changing and where the electrons are changing. So the zinc, we see the zinc goes from having a charge of 0 to having a charge of +2 when it's bound to sulfate. And so that means that the zinc had to lose 2 electrons in order for it to be able to bind to the sulfate ion. Similarly, we see the copper that started off bound to sulfate, but on the other side, it became a 0 charge, and it started off as a +2 charge, which means that it had to gain 2 electrons in order to become neutral or 0 charge. The sulfate ion is -2 on the left and -2 on the right. So it's irrelevant. No electrons are moving with a sulfate ion. The sulfate ion is not giving up or taking on more electrons during this reaction. So it's irrelevant to figuring out the oxidation or reduction. It's really focused on the zinc and the copper. And so because the zinc in the end is giving up electrons, it is losing electrons. The loss of the electrons from zinc is called oxidation. Because the copper is gaining electrons, the copper goes from 2+ to 0. The gaining of electrons means that copper is reduced. However, because the copper starts as CuSO4, you would have to say the C copper sulfate or CuSO4 is the actual thing that is reduced. The entire molecule is reduced, and that's what's separated. So now I encourage you to practice for yourself. Now let's answer it. So first thing you have to do to answer this question is figuring out what's moving. It is easiest for me to figure out first, is it the carbon or the hydrogen that's moving? Because I see on one side it's CO2 and on one side there's O2. So my instinct is to think that the carbon is going to bind to the oxygen to make the CO2, which makes the H2O left over. However, the way carbon and hydrogen are set up, like the overall molecule structure, hydrogen's mad smaller and mad lighter than carbon. And so things that are smaller and lighter are always going to be more likely to move and easier to move because it just takes less energy. So I'm going to assume the hydrogen is more likely to move than the than the carbon, and set myself up for the rest from there. So, okay, I put the hydrogen in red as the thing moving, and then the CO2 is in blue. So those are the things that help me separate them. I can also identify the oxygen goes from just being an element, so it has no charge by itself, to having bonds, aka it's bound to something now. And then in order for the oxygen to have bonds without changing the overall formal charge of the oxygen, that means that the oxygen had to take on some electrons as well. So then from there, I know if one has to be oxidation, the other has to be reduction. So I can go and just split these into their two half reactions, where I have the oxygen becoming the water, or the H2O. And I know in order for this to balance, that has to include the hydrogens moving. But going back to separating hydrogen and electrons, this also means the electrons have to move if this charge is going to stay balanced. So the 6O2 plus 12 hydrogens plus 12 electrons makes 6 waters. So the oxygen gains electrons, which means it is reduced. Good job. In contrast, the C6H12O6 becomes carbon dioxide and releases the 12 hydrogens and the 12 electrons. So because this is losing the 12 electrons, regardless of the hydrogens, it's losing the 12 electrons, which means that it is oxidation. Good job. So now I can just answer these questions. The thing that gained the electrons has to be reduced, and the reducing is from the side on the reactants, not the side on the products. So the thing that is reduced is oxygen. Therefore, oxygen would be the oxidizing agent. I always have to rehearse this in my head as well to make sure that it fully lines up and makes sense. So it's okay if you take a second to check yourself of the oxidizing agent gets reduced, gaining electrons reduction. What gained electrons? Okay. And the product side is not where you're going to see electrons. You'll see it on the reactant side. So then in contrast, the C6H12O6 is losing electrons, and a reducing agent adds electrons to something else and is oxidized itself. So because this C6H12O6 is oxidized, it is reducing something else, therefore it is a reducing agent. Thanks for watching. See you next time.